Hi, welcome back to Caroline's Chemistry. Empirical formulas are a common calculation at GCSE in A-level chemistry, and they can tell us something really useful about a substance. In this video, we'll go step by step through how to calculate empirical formulae from experimental data, whether you're given percentages or masses. We'll look at the method, the common pitfalls, like what to do when ratios don't come out neatly, and a few exam-style questions to make sure you can handle whatever the paper throws at you. By the end, you'll know exactly how to get from data to a correct empirical formula confidently every time. Let's dive in.
Let's start with what exactly is an empirical formula and what's the difference between that and a molecular formula. So empirical formula tells us the simplest ratio of atoms of each element in a compound. So for example, if we have a compound C4H8, then that simplest ratio, 4 to 8, becomes 1 to 2 CH2. Okay, so how's that different from a molecular formula? Now, a molecular formula tells us the actual number of atoms of each element in a molecule. So for instance, that C4H8 tells us that there are 4 carbon atoms and 8 hydrogen atoms joined by covalent bonds in one molecule of C4H8. We do, however, need to go one step further with this because there's a key mistake here that could be made. Every substance, no matter what structure type it has, does have an empirical formula. So here you can see some examples. SiO2, silicon dioxide, is giant covalent. Giant covalent means that we have atoms joined by strong covalent bonds in a giant lattice. The SiO2 there tells us that the ratio, the simplest ratio of silicon to oxygen atoms is 1 to 2. Contrast that to iron iodide, FeI3. That's a metal and a non-metal, so it's ionic. Again, our empirical formula tells us the simplest ratio of ions in the lattice. In this case, because it is FeI3, then the ratio of iron ions to iodide ions in the lattice is 1 to 3. And then we have something like CO2, which is simple molecular. And that tells us that the simplest ratio of carbon to oxygen atoms in the substance is 1 to 2. Only, however, simple covalent structures or simple molecular structures have a molecular formula. So every substance has an empirical formula. Only simple molecular substances have a molecular formula because they're the only substance type with molecules. And they tell us the number of atoms of each element in one molecule. This is the method for how we calculate them, and it's the same method every single time. You start by writing down the elements in the question. And when you do that, make sure that it is the formula of the element on the periodic table. So for instance, if the question is asking about hydrogen, then I'm not writing H2, I'm writing down H off the periodic table. Once I have the elements, I'm then going to write down the information from the question. And it doesn't matter what format they give you that in. Sometimes it's masses, sometimes it's percentages. I'm just going to write the elements and then that data underneath. I'm then going to find the AR of the element and divide each of those bits of data by the AR. Now at that point, technically you have a ratio, but it's not necessarily a very nice ratio. So this next step, step number 3, is about trying to get the simplest whole number ratio. So you find which is the smallest number and you divide all of the numbers by that smallest number. Now I've written careful there in this point because it sounds simple, but it's surprising how many people, how many students actually lose marks by not correctly identifying the smallest number. So double check that one, especially if you're working with like very small numbers like 10 to the minus 3, 10 to the minus 2. Check carefully what the smallest number is. Now, once you've done that, divided by the smallest number, and I'll show you an example of this in 1 second, then you might have your answer. You might have 2 to 3, but you might not still have a whole number. So you might have 1 to 1.5. And if you have that case, you can't round that 1.5 up or down because you can't create or get rid of half an atom. So you might need to multiply up, like 1, 1.5 becomes 2 to 3 to get that whole number ratio. I'd also say once you've done all of that process and you have your simplest whole number ratio, that is not the empirical formula. Put it back into the formulae for the elements. So for instance, if you land with 1 to 3, the empirical formula might be Fi3. So you're taking that ratio and putting it back into the formula. Let's have a look at an example now of how to do this and how to apply this method. So let's work through this method now. I'm going to start by listing the elements. So that is iron, Fe, and O. So just as they are in the periodic table, it's not like O when it is in its natural atmospheric state, which would be O2. I'm listing them off the periodic table. Now I'm going to pop in the data from the question. So I have 72.4% of the iron and I have 27.6% of the oxygen. We're now going to divide by the relative atomic mass, the AR of both of them. So at A level, remember those are given to one decimal place on your periodic table, GCSE's whole numbers. So dividing by 55.8 and 16.0. Once we've popped that into calculators, I'm going to try and keep as much of the number as I can to avoid rounding errors. So 1.292857, and here we get 1.725. Careful, make sure that you decide which is the smallest number carefully, and it's this left-hand one. So I'm going to divide both of these now by the 1.292857. And when we do that, we come out with 1 here. Anything divided by itself is 1. And here we get 1.33. Now careful when you get to this stage, this is not the simplest whole number ratio. You can't just round down and get rid of a third of an atom. And you can't just round up and make up 2/3 of an atom. So instead, we're going to need to multiply up to find the simplest whole number ratio. So timesing by 3 gets us to the whole numbers of 3 to 4. This isn't the molecular formula, it's the ratio. Now write that as your molecular formula of Fe3O4. And that is your answer. That is your empirical formula. So this question is a little different because we have masses, that's not the issue. But one of those masses is for hydrogen peroxide, which is a compound, it's not an element. And I need the masses, the data with the elements. But good news is we can work that out. So we can calculate the mass of the oxygen. Because of the law of mass conservation, which says total mass of the reactants must equal total mass of the products, I can do the mass of the hydrogen peroxide minus the mass of the hydrogen to give me 4.00 grams of oxygen. And I'm keeping those zeros for now because the data in the question was given to 3 significant figures, hence me using 3 significant figures here. Now we can do a normal empirical formula calculation. So those are my elements, hydrogen and oxygen. The data, the masses, 0.25 and 4.00. Dividing each of these now by the AR of the element, so that's 1.0 for the hydrogen and 16.0 for the oxygen. Tap that into your calculator and you get 0.25 for both of them. Now hopefully you can see that that is a 1-to-1 ratio. So the first part of the answer, the empirical formula, is therefore HO. But that's not the end of the story here because we're also asked to calculate the molecular formula. Now we have the MR of the molecular formula of 34.0. I can also work out the MR of this empirical formula because the hydrogen is 1.0, the oxygen is 16.0, so therefore the MR of the empirical formula is 17.0. And I can essentially see how many times this empirical formula fits into the MR of the molecular formula. So I'm going to divide one MR by the other. So 34.0 divided by 17.0 is 2. So I'm therefore going to take my empirical formula HO times it by 2 to give H2O2, and that is our molecular formula. HO is the empirical formula.
Thanks for watching, and if this was helpful, don't forget to hit like and subscribe now for new chemistry videos every single week so that you can do the best in your GCSE or A-level chemistry. I'll see you in the next video.